All right, today we are cracking the code on one of the most powerful ideas in all of engineering, the transfer function. Now, I know it sounds super intimidating, right? But it's actually this really elegant key to understanding how just about any system works. I'm talking everything from the airplane you fly in to the AI that's running on your phone. So let's dive in and see how it's done.
I mean, seriously, think about it. It kind of sounds like science fiction, but it's a very real problem. How do you know for sure that a new aircraft design is going to be stable in the air? Or how a tiny circuit is going to react to a sudden power surge? How can you possibly predict what a complex system will do before you even build it? That's the million-dollar question.
So, the heart of the problem really is how we naturally see the world around us, which is, moment by moment through time. And when you're talking about systems that change and react, the language of time, well, that language is calculus.
Yeah, if you want to model how a system behaves from one second to the next, you've got to use these things called differential equations. They're incredibly powerful for sure, but trying to solve them for anything even slightly complicated can be, and I'm quoting a source here, horrendous. Seriously, it's messy, it's really difficult, and it's not intuitive at all.
So what do engineers do when they're staring down a horrendous problem? Well, they don't bang their heads against the wall. They find a clever shortcut. And in this case, the shortcut is all about changing your point of view. Instead of fighting with the math in the time domain, we're going to take a leap into a totally different world.
I just love this quote I saw on Reddit about this. It just perfectly captures what it feels like the first time you use something called the Laplace transform. You take these nasty, complicated differential equations, you apply this transform, and poof, they turn into simple algebra problems you can actually solve. It honestly feels like math-magic. And this magic is exactly what gives us the transfer function.
And this is the tool that the magic creates. I know the formal definition sounds a little dense, but the core idea is actually pretty simple. You take what comes out of the system, the output, and you transform it. You take what goes into the system, the input, and you transform that. The ratio of those two things, that's it. That's the transfer function. It's one single, clean algebraic expression that holds all the secrets to the system's behavior. So let's just put these two worlds side by side for a second. Over on the left, you've got the time domain. That's where we live, and it's where the math is hard calculus. But on the right, we've got the S domain, this special place created by the Laplace transform. And over here, that exact same system is described with simple algebra. The transfer function lives in this S domain, and believe me, it makes an engineer's life so much easier.
Okay, so once we're in the S domain and we have this transfer function, we can start to decode it. And the cool part is, the algebra isn't just simpler, it actually reveals the system's deepest secrets, its fundamental personality, you could say. And it does this through two main things.
First up, we've got something called poles. You can think of poles as the system's natural tendencies. They're the frequencies or the behaviors the system just wants to fall into on its own. Mathematically, they're the values that make the bottom part of our fraction, the denominator, go to zero, which makes the whole thing just explode to infinity. Poles tell us how the system wants to act when left to its own devices.
And then you have the zeros. Now, if poles are where the system's response goes totally wild, zeros are where it goes completely silent. These are the values that make the top part of our fraction, the numerator, equal to zero. And when that happens, the system's entire output becomes zero. It's like a zero can completely block or absorb a specific kind of input.
So what do we do with them? We plot them. We take these poles and zeros and put them on this graph called the S-plane. A little X marks a pole and a little circle marks a zero. And what you get is this unique fingerprint for the system. An engineer can just look at this map and, at a glance, understand the system's most important characteristics.
But out of everything this map tells you, here is the absolute most critical piece of information. Is the system stable? It all comes down to where the poles are. If all the poles, all those little X's, are on the left side of that vertical line, the system is stable. Any disturbances will eventually fade away. But if even one of those poles creeps over to the right half, the system is unstable. Its response will just grow and grow forever until it literally blows up.
Okay, so we've got this amazing tool that turns calculus into algebra and tells us if something's going to explode just by looking at a chart. But where do people actually use this stuff? Well, the answer is pretty much everywhere. The applications are incredibly diverse.
The classic use, of course, is in control systems. This is how engineers make sure airplanes fly smoothly, how robots move with precision, and how huge industrial plants run safely and efficiently. For them, stability isn't just a nice-to-have, it's everything.
And of course, in electrical engineering, this is absolute bread and butter. As one of our sources from Testbook points out, it's fundamental. Engineers use transfer functions all the time to analyze and design circuits, figuring out exactly how they'll behave long before they ever pick up a soldering iron.
But here's the thing, it's not some dusty old tool from the history books. A paper from just a few years ago, in 2021, shows how researchers are building transfer functions directly into deep learning models. They're actually using this classic idea to build smarter, more sophisticated AI that can understand and model dynamic, real-world systems.
And get this, it even goes way beyond traditional engineering. Some researchers are using transfer function analysis to model and forecast unbelievably complex systems, like the entire economy of a country. That just goes to show you how universal and powerful this way of thinking really is.
So, we've gone from crazy calculus to simple algebra, from circuits all the way to AI and national economies. But what's the one big idea, the main takeaway from all of this? It's really this: the transfer function is so much more than just a math trick. It's like a universal language. It lets an aerospace engineer, an AI researcher, and an economist all describe the basic input-output relationship of a super complex system using the exact same framework. It's a way to model, to predict, and ultimately to design a better and safer world.
And that kind of leaves us with one last thought. The real lesson of the transfer function is that sometimes the hardest problems can become shockingly simple if you're just willing to look at them from a completely different angle. So what hidden behaviors, what simple solutions might be waiting to be discovered in your world if you just changed your point of view?